Okay, so it's a pleasure to welcome Melissa Liu again for the second talk, which is about open-closed mirror symmetry and wall crossing.
Yes, thank you very much. First of all, someone pointed out there were some typos in my talk, so I started to watch my video, but it was so painful that I didn't finish it. So the first example typo when I say the Gobakuma Maha formula. So first a very recent preprint of Yonel Carter provides a proof of this formula. So the formula says if you have a Claudius threefold X and beta is some curve class. Yesterday I tried to isolate the contribution for mixed curve class, and maybe I didn't do it quite right. I confused myself. So let's take the sum over all curve class. So then the left-hand side, on the left-hand side we have this n, capital N, which are grouped within invariance counting parameterized curves. So counting maps, stable maps of genus G and degree beta. These are rational numbers. So on the right-hand side, we have this, I don't know, Gobakuma-Vafa invariance or BPS invariance. This is supposed to count genus G degree beta embedded curves, and they are integers. I think they finally constructed such invariant. And then, so these are this is the multiple cover. So let's see. So for example, we have the resolved conical. Then on the right-hand side, so the only embedded curve we can see is this P1, right? So N0, 1 is 1, everything else is 0. So right-hand side, there's no sum of genus, there's only one term. And then you get this, which is right. Okay. And then, I discount. So about Lobestida Marine, so the open version I checked, so it's conjecture by Lobestida, Marino, and Vafa. So to make sense of their conjecture, so we assume X is a Claudius threefold, and L is a Lagrangian submanifold with Maslov class 0, and assume that H1 is V. Okay. So then we consider, so the formula looks like this. So somehow now we need to fix a bunch of winding numbers. But then in general, if you fix a winding number, there are it doesn't completely determine the degree, which is now a relative homology class. But there's a compatibility condition, right? Because there's connecting. If you have beta, the boundary of beta should be equal to the sum of this. So on the left-hand side, I forgot to say. So these are open remote Witten invariants. They should count parameterized curve in X with boundary in L. And this right-hand side should be count embedded holomorphic curves in X bounded by the Lagrangian L. So here, the left-hand side, the compatibility condition is this one. On the right-hand side, the compatibility condition is this. So if we fix, so now let's look at the simple example C3, and this is L. So the only open curve we can see is with boundary in L is this disk. So we only get 0, and in this case, beta, so the degree is the relative homology class is determined by the boundary. So we only have this one, so we can suppress beta. And then you see, if you fix to be D, you are fixing the relative class 2, so there's no sum over beta. And on the right-hand side, you just get, this, right? So this, which is right. There's a negative sign, but this, I think that for open Gromov within invariance, the sign depends on how you orient the moduli made, which is not so canonical. Okay, I just want to make these corrections. So now I can start with today's topic. So today I want to.
Let me just say, so for example, change the almost complex structure. So did you expect this is invariant?
No, I don't know if this is invariant. I'm stating a conjecture made by other people.
Okay.
So okay, so let's symplectic polynomial threefold. Our main example will just be the result conical and local P1. But in general, this can be constructed by symplectic reduction. So you have some axon vector space of P plus 1 dimensional, and then you can consider there's a maxima compact, and it's Hamiltonian with respect to the standard symplectic structure on CP plus, let me do CP plus 3. Then your, so then you choose some, so you have a, so this gives you, so you have a moment map from CP plus 3 to RP, the dual, the Lie algebra of this, and you can construct your X by, so together with the symplectic structure by symplectic reduction, this can also be, so this eta also gives you some stability conditions, so it's a GIT quotient. And so in general, so if we assume this is smooth, this is a free action. Okay, but then we will mostly just talk, so I'll show you some simple examples, but the results will hold for general Torrey-Calabi threefold. So for example, for example, we consider C star X on C4 this way, say 1, 1, minus 1, minus 1. Then this mu T tilde, so coordinates on, so this is with respect. I didn't divide that, so I think this is right. So this is the moment map, and then you can, if eta, also in this case, here T is just U1, and given by this, and when eta is greater than 0, then T inverse eta is, so these two can now be both 0, but these two can be anything. I should say. So this gives it symplectic structure, but then if you just care about the complex structure, so this is the result conifold. differ by a T of graph. Yeah, so we have some wall crossing when eta is 0. Second example. Second example is X on C4, but with weight 1, 1, 1 minus 3 instead of that. Then this is the Roman map, and you see that when eta is greater than 0, the symplectic quotient so this cannot be on 0. Yeah, so with this way, this is total space of O minus 3 over P2. It's a smooth toric Claudial threefold. When eta is less than 0, then you see the last component cannot be 0. But then you can fix this to be 1, then this will reduce to, so this is, and then these 3 acts on diagonally, so okay, so this is a singular toric Claudial threefold, but it's synclition. It just has orbital singularity at one point, and when you can blow it up, and this is a Perkin's resolution. Yeah, so there was some like wall crossing, like in there, Roman rectangular. So yeah, that's your X. 2 examples. So for general X, you have this compact 3 torus actinate, and it's convenient to consider the prime. So T prime X trivially. Okay, assume your Claudial threefold has at least one fixed point. Then at the fixed point, your torus act on the fiber, act on this fiber. So we assume that, so there's a 2-dimensional subtorus acts trivially. So this is, we call it the Claudial torus. So this is independent of choice of the point because of the Claudial condition. So then, if you consider the moment map from defined by P, the image is R3, right? So this is like projected to R2. So then you get some graph. So you consider, so this is a union, one scaling of 0 and 1 dimensional orbit. Then you consider this one. So this is epsilon graph. Okay, so I'll just do it for these two examples. This is a zero section P1, and this is the fiber over 0 is a copy of C2. These are the two one-dimensional orbit closure in that fiber. And similarly, we have. So this is the P2. So these are the three torus fixed points in P2. Yeah. Okay, this is the fiber over this fiber of this bone over this fixed point. So yeah, so maybe let me give this graph a name. So this also depends on omega because so this is right. So this projects down to here, and the length is proportional to the symplectic area of this P1, and similarly we have yeah, also, so this is due to if you consider the fan and intersect, you can arrange that like all the generator of the, yeah, so the fan intersect, so the fan is a cone over this picture. So this already appeared in the previous talks. So this is 0, 0, 0, this is 1, 0, 0, 1, and minus 1, minus 1. So these are our two main examples. And you see like what is like this wall crossing is like when eta, so this is so when eta goes to 0, then yeah, so you see when eta goes to 0, and then finally this comes. This is so this is a simplicial tori variety defined by the cone over this polytope. Okay, so then this polytope will be the Newton polytope of some Lorentz polynomial, right? And then we want to, so actually this will be, so the mirror curve of x is just yeah, this is a fine curve. And the shape of the mirror curve is just like the fattening. So this, yeah, so maybe if I call this mirror curve, C, it's genus 0 with 4 punctures, genus 1 with 3 punctures. And what happens when we shrink this? So this is this is the amoeba, but when you shrink this, you cannot see the hole here, but the hole is in some other direction. So the mirror curve of the mirror curve of C3 mod Z3 is still a torus with 3 punctures. It's just you cannot see the hole when you project down to the amoeba. Okay, that's the picture. So maybe I'll just do so more generally, if you have you consider this so this Cm plus 1, so this acts on the fiber. So let me call this, so this is singular, and you can also consider the resolution. So I think this is, either of this should be large and still like S3. Yeah, maybe this is what you claim. Okay, and then this is okay. So yeah, the resolution. So yeah, actually, so this is. And the resolution is like this. Yeah, I guess I'm drawing the case. Sorry, this is M. Yeah, so this is, I draw the case where maybe I'll just draw Y3. So then I have, oh actually, Y2. And then we have this is the and then the mirror curve is genus 2 in this case. And if you do N, then you have genus M. Okay, so these are examples. So then for such polyclavial threefold, there are I think there are 3 mirror families. So the first is yeah, so it comes in families. And actually, if X is so then P in the smooth case, this is equal to the second Betty number, which is also than x cubed. So this is some homomorphic string form which is explicit, and this is okay. So horizontal mirrors can be constructed by applying SYZ to the gross vibration, and many people in the audience made contribution. So then there's another mirror is usually like this toric. For in general, if you have a toric variety, so you have this Landau-Ginsburg model, but it's non-complex. So let's consider the equivariant. So this is equivariant. So this is it has three variables. So if you restrict to t prime, so this is by setting this, this is so you see if you don't have this equivariant perturbation, then it's like if you look at a critical point, so suppose that hxy is a smooth curve, then the critical point is empty. So we do the equivariant version. And actually, so now the thing is, so we might need, so later on I'll explain that, so in this, so if you have such a, so in general, you have,
What's the equation for x check? There should be a UV.
oh yeah, well, yeah, you're right, sorry. Yeah, thank you. So, yeah, so this hypersurfacing, thank you very much. And this should be like this. So this is a hypersurface in here, which is a non-compact Labial string. So it's, so it can be viewed as the complexified, so this is can be viewed as the complexified moduli of fibers of the gross vibration. So by dualizing the fibers of the gross vibration. Okay, and then, so now we have this mirror curve. So the thing is actually, we are going to, it turns out that so this can be, there's some dimensional reduction. So there's a dimensional reduction. Mathematically, if you have like genus zero, we know like genus zero theory, like B model, genus zero B model, like is determined by the period integrals of this holomorphic string form. It turns out that these period integrals can all be reduced to, so this is multi-value, but the period integrals here can be reduced to, maybe let me call it B. So integral of this one form over loops. Okay, so the theory here, so the B model theory here can be reduced to a theory of at least in terms of like genus 0 enumerative predictions. And moreover, this so this Landau-Ginsburg so we need to restrict to some one-dimensional torus. Then this can be reduced to, so this is Landau-Ginsburg model. This can actually be reduced to Landau-Ginsburg model CQX. So CQ, so X is a coordinate. So so Bo's theory can be reduced to a theory of the narrow curve. Yeah, so like in the following, we will just describe the mirror symmetry in terms of the narrow curve. But yeah, because we need to use the like a toric mirror theorem is proved like in this context, so we need to have a precise relationship. Okay, so now okay, so we want to say that actually, so we want to consider open remote within invariance with relative to a particular nice class of Lagrangian submanifolds. So this is construct as follows. So suppose that, yeah, so I'll just do by example. So you see this is like so the moment polytope of the resolved conical when you project like this. So then so you consider a ray. So this ray will project to a point. So this corresponds to a ray ending in, so the end is at an edge but not a vertex. Then here, if you look at, so here this, under the, your L is mapped to here, and then the preimage here is a 2 torus, and preimage here is a circle, so this is a circle come over a circle, which is, so we will only consider, yeah, this Lagrangian submanifold of this type, and this construction works for any toric Labial stringfold. We just take the ray, and it's, yeah, and then you see that, so what is the moduli space? Then the moduli space of this Abnegi-Bava brane is just this graph, right? Because you pick a point, and there's some problem here. Here you get some singular. But then, given a point, you get the Abnegi-Bava brane. So it can be viewed as, so this is the, so the moduli of Abnegi-Bava branes. But you want to classify it, so given a Lagrangian submanifold, you want to equip it with a flat U1 connection. So this will give you, the choice of U1 connection will give you the complexified mirror curve. So yeah, so the mirror curve is exactly the complexified moduli of Abnegi-Bava branes. So it's one-dimensional because the first Betti number of this is one-dimensional. If you do like torus, you get three-dimensional space. And then I want to say, so given an Abnegi-Bava brane, give us a reparametrization of the mirror curve. So there's a general procedure, but maybe it's just, I'll just give you some examples. So these are different phases in this open string moduli. So if your imagined Baba brain is an inner brain intersecting the P1, then the equation is then if you for example, you know you have this configuration upstairs, right? So if you choose a point here that corresponds to a negative alpha brain looking like this. So I'll write down okay, so now so we will define B model. This potential defined in terms of the just in terms of the frame mirror curve. So f check 0, 1, qx. So what is q? So actually you see like this is the, okay, I'm sorry, in general this is my hxy, but it comes in families and the complex parameterization is q. Here it has only one Taylor class, so we only need one variable. So this is hy, it depends on q. So then you see, say you are in this space, so you should think that this, yeah, so this is equal to,
Sorry, Melissa.
yeah.
Doesn't Formula 1 on the top board have an extra term that shouldn't be there?
Oh, where? Which one?
The number 1
Yeah.
has 5 terms. I think it should only have 4 of
Yeah,
them.
you're right. This is not right. So I think this is. Yeah, thank
Doesn't look right either. Sorry.
you. Yeah, yeah, right. You're right. So, yeah, then it.
Okay.
So I hope I didn't copy it wrong. So, but in the paper it has examples. It has all the, you replace P2 by any solid panel surface with the formula. And there's a general algorithm to write down this in each phase. Yeah, so the idea is the following. So if you look at the outer, so suppose that you want to understand, the Dixie invariant with respect to this Lagrangian. Then what you do is you look at this neural curve, and so there's a projection to C star. And near this point, this log y is actually y is near this point is not 0, and near this point, it can be extended to here, and this is a good coordinate near this puncture. You can compactify it, and then there will be a power series solution of this. So so this is, and then you take the power series solution and you do this. So the only problem is if there's a constant term when you integrate this, there will be a logarithm. So there will be something log x plus, let's call it the incident part. Okay. So then we also have, in this case, which we have actually defined for, so this is, this is the winding number. Yeah, but this number depends on f. If you like, you choose, so different f give you different bounding coefficient, so you should get different numbers. Yeah, okay, so this Q beta Z W. So then the conjecture by magic alpha and magic sem alpha says that so these two are equal under open shows zero map. So here you know that if you take the absolute, so you should think so this is like the Novikov variable, this is like the open Novikov variable. So you see when you approach, so you can think, suppose that this area, so if you take the absolute value of z, this is like exponential minus area of this. So this tends to 0 when this area becomes very large. So when you move this to very far away, this corresponds to like when you approach the puncture. And near the puncture, you have a power series expansion. So A model potential is just formal, but B model this potential has a power series expansion in X, which converts at like when the absolute value of X is small. So this tells us the convergence of the A model. And you see that you already see there's some wall crossing in this open string moduli. When you fix Q, right? So you see what happens when you move. Yeah, mirror crossing. So in this case, the open string moduli is just, this actually depends on, so this also depends on some parameter Q. So then you can see that because you have this, suppose that you have this objective buffer brain in phase 2 and it's very far away, so that you have this potential. So okay, for the resolved conical, so the mirror map is the identity. So big Q is equal to little q and big X. This will correspond to the open non-equal variable. So for resolved conical, they are just identical. So the D model, this potential is equal to the A model, this potential. So in phase 1, yeah, maybe this is. Maybe it's not. So there's some. Yeah, okay, so it makes sense, right? Because in phase 1, you are expanding things like, so you're expanding this near puncture of the mirror curve, so you get a power series. That is correct, because you can only get positive winding number, so you will get a power series. So this is phase 2, you get a power series, W is non-negative. But in phase 1, you are actually, this expression will be a Laurent series. It has positive, negative powers. And as you can see, because you can have positive and negative winding number coming from these two disks. Okay, so that's the, and there's a wall crossing because you see as you move close to this point, at some point your x, the absolute value x becomes so large that it diverges. So this is the wall crossing in the open string module. So maybe, so here we also have, so here is x is, so in this case, the, so the closed neural map in this case, it's so this is 0 when Q is 0. And the open mirror map and log x is equal to yeah, because in different phase the different x so this in different phase the mirror curve are all like isomorphic, but our coordinate x are different. So then so in phase 1 open mirror map is phase 2, phase 3. And also, yeah, so you can, there is also explicit expression f. Maybe like I'm running out of time, so I won't write down. But yeah, for any phase you have like it's given by explicit power series solutions. And the mirror map is also given by explicit power series solutions. So how about the walk? But then you can also do walk crossing. In the closed string moduli, right? So because then of course, if you don't know what happens in phase 1 and 2 because this P2 just disappears. But you can discuss, so suppose I have this phase 3, right? So here I still have this. So this blow up doesn't touch this Lagrangian. So actually, so then now phase 3. Oh, actually, I forgot to say that the conjecture has been proved. So here, this is C3. So we have a, maybe I should say that AB conjecture. So the smooth case is by Goldman and myself, and later it's extended to orbital case. So we also know how to write down this frame mirror curve for in the orbital case, and I'll just show you in the orbital case. So this Q hat is the extended Kähler moduli of this orbital, and X hat is the like open string moduli for it. And you see they are, so these two equations are just related by the change of variable. So this tells you if you see then from here to here that this function has a walk crossing in the open string module. Of course, Still Chung, Lau, and collaborators prove like much more general case. But we also know what to do, so, like when your Lagrangian is Derby and in the resolution you have several Lagrangians corresponding to the same Lagrangian. We also know how they are related. Also, finally, I will just say very quickly that this can also be extended to so there is this determined by A cycle, and we choose our A cycles. So we can choose A cycle such that the integral of this one of that one from log y dxx give us the neural map. That's how this is fixed by. So then. So this is construct. So define recursively by the Anna-Orenton topological recursion. And then somehow the disk. So then if you I'll just say that. So the B model FGN, so I'm running out of time, is determined by expand So in local coordinates, this will be like, so in the stable case, so locally, so in this coordinate view x1, so of course this also depends on q, and then your FGN is basically given by integrating, so this is the B model. B model higher genus open potential. So and then so this under open closed neural map. So this is conjecture by EKMP, and in the smooth case, is proved by Aina and Orenton. In the orbital case, it's proved by Fang and myself, and so okay. Yeah, thank you.
Any questions or comments?
So how do you prove the orbital case?
Oh, so in the orbital case, so yeah, so here this DOS. So this is topological recursion has a graph sum formula. It has a unique solution. So there's a graph sum formula of the solution. And here, so first there's a on the right hand side. So we use like the quantization formula for equivariant remote Witten of the torus symbol. Smooth case is due to given topological case is due to zone. And then you need to use that and change the descendant leaf to open leaf. So it's a combination of like you get a graph sum formula of this open potential using the quantization formula for descendant potential plus the neural theorem of the disk, and you get a graph sum formula, and then you compare each graph, and they are equal. Yeah.
Is there some kind of even heuristic argument for exactly what's happening to the moduli spaces of disks as you move this point along, through the vertex into a different phase?
So here, so it's when you move, then this because you are changing the so x equals when you form this generating function in the closed case let's just forget about, so this, for example, this Q beta is like, right. Yeah, right. So then this X is also, so this Z is just, yeah, I think in this case it's just the area of this disk. So when you move, this Z changes, at least for the, if you, and there's a holonomy, which is the imaginary part of this. So say this is alpha. So if you have winding number W, then you get Z to the W's power. And as you move like when this becomes smaller and smaller, your power series like diverges.
Okay, if there's no further questions, let's thank Melissa again.